Section 1.7, Inverse Matrices. The objectives are: define the identity matrix, find the inverse of a square matrix if it exists, use inverse matrices to solve systems of equations, and finally to solve applied problems using inverse matrices. We begin with the definition of an identity matrix. An identity matrix is a square matrix denoted by either I or IN, and the special thing about the identity matrix is it has ones along the main diagonal and zeros everywhere else. So an example of that might be I2. So I2 refers to the fact that this identity matrix has only 2 rows, and as you can see, there's ones on the main diagonal, but there are zeros everywhere else. Another example of this is I3, the identity matrix with 3 rows. And again, there are ones on the main diagonal, and there are zeros on the rest of the matrix everywhere else. The important thing to remember is that the identity matrix multiplied by any other matrix will result in the original matrix. And so let's go ahead and see that with example number 1. We're given a matrix A, and we are expected to multiply A with I, then I with A. Now, because this A is a matrix of size 2 by 2, the I that we're talking about in this problem is I2, which is this one over here. So let's begin by performing the product of A times I. So A is 4, 5, negative 2, and 3. And we want to multiply that by the matrix I, which is, in this case, 1, 0, 0, 1. In the previous section, we learned how to multiply this. So I'm just going to follow along and do the same steps we did before. I'm going to grab the first row and multiply with the first column. And so to do that, I'll just write in little pencil notation 4, 5 right there and multiply the answers. 4 times 1 is going to be 4, and 5 times 0 is going to be 0, and 4 plus 0 is going to be 4, so let's just write down 4. So that's how we get the first entry of the solution in this case. If I want the next entry, which is the first row, second column, I'll take the first row and second column and I'll multiply those with one another. So again, like we did before, we'll take our pencil and we'll write 4, 5 on this side, and we'll multiply 4 times 0, which will be 0. We'll multiply 5 times 1, which is 5, and add up the answers. So the answer is going to be 5 again. And we proceed in the same way to get the rest of the numbers, and the other numbers will be negative 2 and 3. And as you can see, the answer that we got is the original matrix that we began with, 4, 5, negative 2, and 3. Now, if we perform the product in the opposite direction, in the fact that we put I first and then A afterwards, that means we're putting 1, 0, 0, 1 first and multiplying it with the matrix A, 4, 5, negative 2, and 3. In general, multiplication of matrices is not commutative, but we'll see that when you multiply with an identity matrix, the product is in fact going to be commutative. We should get the same result as before. So let's multiply the first row with the first column. So again, I grab my pencil, I put 1, 0 there, and I multiply 1 with 4. The answer is going to be 4. Multiply 0 with negative 2, you get 0. And add up the 0 with the 4, you get 4 back. And in the same way, we continue to do the rest of the entries, and you'll see that the answer will be again 4, 5, negative 2, and 3, which gives us the same original matrix A again. So these guys right here are the original matrix that we began with, the matrix A. That's the special thing about the identity matrix. Now, let's talk about the multiplicative inverse of a matrix, or just the inverse of a matrix. So given a matrix A, the inverse matrix is typically called A to the power of negative 1, or A inverse, and it is another matrix that when multiplied with the matrix A gives us back the identity matrix. So in other terms, if you multiply A with the A inverse, the answer is going to be the identity matrix. Or another way of saying this is to say that if you multiply the inverse matrix with the original matrix A, the answer will be again the identity matrix as well. In general, we're interested in finding the identity matrix, but for now, for example 2, they're asking us to confirm or deny whether these two matrices A and B are inverses of one another. So to do that, we'll just multiply A and B and see if the answer turns out to be the identity matrix. So let's go ahead and check. Is it true that when I multiply A and B, I get the identity matrix? So let's find out. So 4, 5, 2, 3. and we are supposed to multiply that with 3 halves, negative 5 halves, negative 1, and 2. So as a reminder, we can do this with a calculator, so let me show you how to do that. So to begin, we have to enter the matrix A and B into the calculator. So we're going to enter the matrix menu, then move over to find edit, and we'll edit matrix A, which is a 2 by 2 matrix with the entries 4, 5, 2, and 3. So this is my matrix A. Once I've entered it into the calculator, I'm just going to quit this menu and go back in one more time. And this time I'm going to edit matrix B. So in other terms, I'm going to put the numbers of matrix B into the calculator. This is again a 2 by 2 matrix. And the entries in that matrix are 3 halves, then negative 5 halves, then negative 1, and finally 2. Notice that the calculator automatically converts everything to decimals, and the important thing to remember is that when you're entering any negative values in this case, you'll have to use the small negative sign on your calculator. Once you're done, you can go ahead and quit, and to multiply the two matrices, we'll just enter the matrix menu, call the name of A, which is in this case 1, and multiply it with the matrix B, which is in this case the second one, and hit enter. And as you can see, the result is 1, 0, 0, 1, which is the identity matrix. Now, if the two matrices are inverses of one another, we should be able to get the same result if we multiplied matrix B first with matrix A second. And again, as you can see, the result is the same. So whether you do A times B or B times A, the answer will be 1, 0, 0, 1. So let's go ahead and record that here, 1, 0, 0, 1. And so this is the original matrix I2, which we call identity matrix 2. In the same way, if you want, you can confirm that B times A will be as well I2. So because the result is always coming out to be the identity matrix, we can say that A and B are inverse matrices. Find the inverse matrix given an original matrix. So suppose I have the original matrix A and I want to know the inverse matrix A inverse. How to do that? For now, let's begin by using the formula that's provided to us. So it involves finding some random number that goes in front. We call that the scalar. And then it involves swapping some numbers inside of the matrix. So if a matrix looks like A, B, C, D, the inverse matrix will be 1 over AD minus BC. So we're supposed to multiply those two numbers, and subtract. Then we are supposed to move some numbers around inside of the matrix itself to get the inverse matrix. So given A as 1, 5, 4, 10, the matrix A, then little a will be 1, little b is supposed to be 5, little c is supposed to be 4, and finally the small d is 10. So if I want to know what A inverse is, I'm supposed to first put 1 divided by the product of AD. So if I multiply A and D together, I'm going to get 1 times 10. Then I'm supposed to subtract the product of BC. So the product of B and C, that's going to be 5 times 4. And inside of the matrix itself, what they want me to do is to swap the location of A and D. So the A used to be in the top left corner. I need to put it in the bottom right corner. So in other terms, A will be placed in this corner and D in its place. And for the B and C, I'm supposed to take the original values, but just negate them. So the original B used to be 5. I'm supposed to put negative 5 now instead. And instead of the original C, which used to be 4, I'm supposed to put negative 4. So this will be the A inverse. And let's go ahead and clean it up a little bit. So the inverse matrix will be 1 over 10 times 1 is going to be 10. 4 times 5 is going to be 20. So that total is negative 10. And inside we will have the numbers 10, negative 5, negative 4, and 1. And if we want, we can take the scalar value and multiply it all the way inside into every entry. So that means that A inverse will be a negative 1 because negative 1/10 times 10 is going to be negative 1. Then negative 1/10 times negative 5 will be just simply 1/2. Then we'll multiply negative 4 with the negative 1/10. The answer is going to be positive 4 over 10. That's the same thing as 2 over 5 when you reduce it. And finally, the negative 1/10 will be multiplied with the 1. That's going to be negative 1/10. So this is the result of the inverse matrix. And so as you can see, doing it by hand is not too difficult, but I want to show you also how to do this with a calculator. And so we'll try it out. Let's go ahead and enter the values of A into our calculator and figure out if we can get the A inverse to show up on our calculator screen. And as usual, we will begin by putting the numbers into the calculator. So I'll edit matrix A, which is a 2 by 2 matrix, with numbers 1, 5, 4, and 10. So once my calculator has saved all the numbers and I've confirmed that everything's correct, I'll go ahead and leave this menu. And all I need to do now is just type the name of the matrix on my screen by recalling the matrix A, and then just clicking the same button that we use to enter the matrix menu. So this time though, I'm not going to click second, I'll just click the x to the negative 1. But there's a chance that some of the numbers that appear on my screen are going to be decimals, so therefore let's click math and 1 to turn everything into fractions. And there we go. The numbers are -1, 1/2, 2/5, and -1/10, which confirms what we found previously by hand. So that's one way to do it with the calculator. I want you to pause the video at this moment and see if you can get the answer for part 2 of this problem. See if you can get the inverse of the matrix M, and we will show how to do this with a calculator next. And we begin as usual by plugging the numbers into the calculator. In this case, I've already entered -2, -4, 1 and 0, which are the values that were provided in my matrix M. Notice I'm using the letter A to refer to the matrix on my calculator. There is no letter M for me to pick, so I'm just calling it A. Once I've entered everything, I'm going to quit and call the name of the matrix to my screen, then type in the power -1, and in case there's any fractions, I don't want to see decimals, I'll just hit math 1 to get fractions on my screen. So the answer will be 0, 1, -1/4, -1/2. So let's confirm that this is the same solution that we would get by hand by doing the same process that we did for part 1. So I'll begin by writing down that little a is -2, little b is -4, small c is 1, and d itself is 0. So for the inverse matrix of M, first we'll type 1 divided by the product of AD. So we're supposed to multiply those two numbers, -2 with 0, and subtract from that the product of B and C, which is 1 times -4. And next we will write the entries within the matrix. So according to the formula that we have in this page, D and A must be swapped. So I put D first, then the A, and the corners on the main diagonal. And B and C will be switched around from positive to negative or vice versa. So B used to be -4, it will be now 4 in the new matrix, and the original C used to be 1, so I'll put -1 into my new matrix. And we'll clean this up a little bit to see if we get the same entries that we had on our screen. So first of all, 1 divided by the whole fraction here will be just 1/4. And inside we still have the entries 0, 4, -1, and -2. Then we need to perform the scalar multiplication. So 0 times anything is 0, 4 times 1/4 is going to be 1, then -1/4, then -2/4 will be the same thing as -1/2. And that is the conclusion of the problem. As you can see, we get the same exact numbers that we saw on our calculator screen when we do this process by hand. Now, in case you did not catch how to do this with the calculator, I've written down the steps in this page, so take a screenshot of this or pause the video to write them down. But at this point in time, I'd like you to confirm that you are able to do this on your own by checking for the inverses in example number 4. So we're provided two different matrices, one which is a 2 by 2 matrix and another one which is a 3 by 3 matrix. See if you can find their inverses on your own without looking at the rest of the video first. And here are the solutions. I hope that you got the same numbers. So for A, we already know the inverse. We've kind of done it before. But for the matrix M, it's a 3 by 3 matrix. So just to show you how I did that, I put in the numbers of the matrix into my calculator, 1, 0, 3, -2, 4, 7, 5, -2, 1. I'm using the letter C right here for whatever reason. It's just your own preference. You can pick whatever you want. And when I leave this menu, I just type the C to the power of -1 to get the inverse, and I hit it with the command fraction just to turn everything into fractions so that we don't have any decimals on the screen. So let me show you that. So first I called the name of the matrix. I'm calling it C this time. Then I give it the power -1. And if I stop right now, then you'll see there's a lot of decimals on the screen and it doesn't look right. I have to kind of scroll left and right to be able to see everything, and we don't like decimals in general. So instead, I'll just do this. Matrix C power -1, so that gives me the inverse. Then I give it the command fraction afterwards to turn everything into fractions. And it looks nice and pretty, it fits on the screen, and you're able to copy all the numbers quickly. So you may be wondering, why do I care about this inverse matrix business? And the answer is, we can use inverse matrices to solve systems of equations. So we already know how to solve these systems using elimination, substitution, graphing. In the previous section, we learned how to do it with the row echelon form or the reduced echelon form. And now we just have another new option to solve the problem. And so to solve this problem, we need to rewrite this particular system in a brand new way, not the augmented matrix method, but a new method. So here's how we're going to do this. First, we're going to think of this as two separate problems. We're going to think of the matrix that contains the values 3, -2, 5, 3, and then we're going to think about another matrix that contains the values 11 and 12. So on one hand, I'm going to copy the coefficients 3, -2, 5, and 3 into their own matrix. And then I'm going to write the matrix that contains the numbers 11, 12 on its own after the equal sign. And finally, I'm going to put a tiny little matrix x comma y. This represents the unknowns in my problem. X comma y are the variables, the unknowns in the original question. So what I'm doing is basically kind of writing something that looks like the augmented matrix, except it has an equal sign this time, and it has this new matrix x comma y in the middle. So this is the variable matrix, and in general, we can call it big X. And so typically you'll see the as the matrix A, which is the coefficient matrix. Typically speaking, this matrix is called capital B. So I've turned my original problem into what's called a matrix equation. And the idea is I want to find what this missing X is. And so to find it, I need to get rid of the A. And in the matrix world, there is no such thing as dividing two matrices, but what we will do is we will multiply it on the left side by the A inverse. We know that A inverse multiplied with the A will be the identity matrix, and then the identity matrix multiplied with the X matrix will be the X matrix. But because we're multiplying on the left by A inverse, whatever you do on one side of the equation, you're supposed to do the same on the other side, so you'll multiply the other side by A inverse. And the result will be that the variables that you're looking for, which is what we're calling the big X matrix, will be the product of A inverse with the matrix B. So the key here is that there's an inverse matrix in the solution. So if we can find the inverse matrix for A and multiply it on the left with 11 and 12, then we will have our answer for x comma y. So that's the idea. That's why we care about these inverse matrices. So I'll just leave this here for you to kind of look at. But now let's go into actually do the process. So first of all, I know that A is 3, -2, 5, 3. So what I'm going to do is look for the A inverse using my calculator. So let's go ahead and edit the numbers. We're going to put them into matrix A into the calculator. It's a 2 by 2 with the numbers 3, -2, 5, and 3. So there we go. Once we are done, I'm just going to leave and enter the matrix B into my calculator. The matrix B contains 2 rows but only 1 column, so this is what we call a column matrix, and the numbers there are 11 and 12. So let's go ahead and type them into the calculator. This is 11 and this is 12. And we will finally go back to the main screen and let's look for the A inverse matrix. So matrix A, I want to know its inverse, and if there's any decimals, I want it to be fractions. And so there we have it, 3 over 19, 2 over 19, and so on and so forth. So let's take a minute to record this on our page because your homework will sometimes ask you for this. So finally, to find the X matrix, which consists of the values X comma Y that we're looking for, we'll have to multiply the A inverse matrix with the matrix B. And again, we can do this by hand, but I prefer to use the calculator here just so that we can finish this problem quickly. So all I need to do now is take the product of A inverse and multiply B to the right of it. So A inverse must be on the left, B must be on the right. Remember, the multiplication is not commutative, so the order does matter. And we already have our A inverse on the screen, so I'm just going to hit it with multiply by the matrix B, which is the second matrix in my entries. And let's go with math 1 to turn everything into fractions. And so the solution will be 3, negative 1. So my answer here is 3, negative 1. So in other terms, what I'm saying is the pair x comma y that satisfies all the equations in this problem is the pair 3 and negative 1. So you might be wondering, it's not much faster than the other methods that we learned. It involves doing more steps, and you might be correct. You might be right in saying that, but this is just another way of doing the math, and it's always helpful to know more than one method because sometimes one method works really good for certain types of problems, whereas another method might work better for those problems. So if I want to do this problem again using the previous section's information, I will have to just put 3, negative 2, 11, then 5, 3, 12 into my calculator as an augmented matrix, then just ask for the RREF. So let's do that next. So first, type in all the entries in the augmented matrix, 3, negative 2, 11, 5, 3, and 12. Once you finish, you're just going to quit, then go back into the matrix menu, do some math on the matrix, and so I'm looking for the RREF option, which is this one, and I'm going to give the name of the matrix to this RREF command, then I'm going to tell it to make everything into fractions if there's decimals. And as you can see, the answer turns out to be, again, x is 3, y is negative 1, just like we predicted before. So why would you choose the inverse matrix option versus the augmented matrix option? Well, maybe your calculator does not have the REF or the RREF command, and maybe this is the only way to do it, so you can't use RREF like I did. Maybe you have an older generation TI or something else, I don't know. So there we go. Now we have another option. So let's continue along and do part 2. So again, I have a matrix, I have a linear system of equations. I'm going to turn this into a matrix equation. So the way to do that is first make sure all the x's are lined up, make sure all the y's are lined up, and the z's are lined up, and everything after the equal sign is all lined up. And we'll turn it into a matrix equation by putting the coefficients, which are 1, negative 1, 2, and 2, 1, negative 5, then negative 1, 3, negative 4 into the coefficient matrix. The second matrix that we write is the variables of the problem. In this case, the variables are x, y, and z. And it's all supposed to be equal to whatever we had after the equal sign, which in this case is 6, negative 11, and negative 12. So in the matrix universe, this guy here is called the matrix A, this guy here is called capital X, and this guy is called capital B, the matrix B. And so we're trying to solve this equation, AX equals to B. In geometry, in algebra, we would divide by A, but in this world, there's no such thing as division of two matrices. So what we do is we multiply on the left side by A inverse. And whatever you're on one side, you're supposed to do the same thing on the other side. This turns into an I matrix, the identity, and identity times X is just going to be X, and it's going to be A inverse B. So in other terms, to solve the problem, all I have to do is multiply A inverse on the left with the matrix B on the right. So the difference between this one and the previous one is just it's a 3 by 3 matrix, so we have to be a little bit more careful typing it in. But let's go ahead and then use our calculator to find what the answer should be for the product of A inverse and B. So first of all, I'm going to write A is 1, negative 1, 2, 2, 1, negative 5, negative 1, 3, and negative 4. That's the matrix A, the original A. So then what is the A inverse going to be? It's a good idea to always write this down, especially because your homework will ask you for the A inverse. And so let's go ahead and search for it using RTI calculator. Okay, once you've completely entered the numbers into the matrix of your choice, in this case I'm choosing the name A, you're going to quit, then you're going to enter the matrix menu, type in the matrix name, inverse, then math 1 to get any decimals to become fractions, and there's my matrix A inverse. So I'm just going to take a moment to transfer this from the TI to my PDF so you can have it for the record. Once you have finished transferring it, we are going to perform the product. So I need to get X by performing the product A inverse times B. So I haven't put in B into my calculator yet, so it's time to put in B. And remember, B consists of the numbers 6, negative 11, and negative 12. And finally, we go back to the main screen of the calculator, and we already have the A inverse on the screen. If you accidentally erased it or got rid of it, it's not a problem. Just go back and type in the A inverse name first and multiply it with the matrix B. And if there's any decimals, I don't want to see them. I'd rather see fractions, so I'm going to ask for the fraction solutions. And there we have it. 2/3, negative 2/3, and 7/3 is the final answer. So this means that the x, y, z triplet that we're looking for, which is considered to be the solution of this problem, consists of the numbers 2/3, negative 2/3, and finally 7/3. And so finally, it's time for some applications. So in example 6, we are told that a company has 3 machines that manufacture custom hubcaps. Altogether, the machines can produce 100 hubcaps per day. The 2 fastest machines together can make 80 hubcaps per day. The fastest machine makes 34 more per day than the slowest machine. How many hubcaps can each machine make per day? So let's start by giving some names to the missing values. So we have a fastest machine, and we have a fast machine, and we have a slow machine, and they're all working together to make hubcaps. So let's say that the slow machine is Z, the fast one is Y, and the fastest is X. So we're looking for the number of hubcaps produced by each machine, and we're calling the number that the fastest machine makes X, and so on. Okay, so first, we know that the machines can make 100 hubcaps per day. This is all together, every machine working at the same time. So in other terms, X and Y and Z all together will be 100. So that's my first equation in this problem. Now, we also know that the 2 fastest machines together can make 80 hubcaps per day. So the 2 fastest ones we're talking about are X and Y. Those are the fastest machines. So together, they make 80 hubcaps per day. All right, and finally, we know that the fastest machine makes 34 more per day than the slowest machine. So the fastest machine and the slower machine are being compared, and we know that the fastest one makes more, but how much more? Well, it's 34 more than the slowest one. Sorry, the slowest one is Z. Okay, so the slow one plus 34 will be equal to X, which is what the fastest machine is making. So this is my linear of systems. but it doesn't look right because, first of all, this z is in the wrong place. So let's move the z over here and rewrite the problem with matrices. So first, I'll write x plus y plus z equals to 100. And notice how I'm spacing everything out so I can remember that the coefficients are 1, 1, 1, so that I can put it into my matrix later on. The next equation is x plus y equals to 80. There's no z there, so I know that there's a 0z there. It's not written down, but I'm just going to remember that for the future. And finally, x, there's no y in this equation. There's a minus z because we're moving the z across, and it's all equal to 34. So these are my equations, and as a system, it looks fine, but I will need to translate it into a matrix equation. So for the matrix equation, I'll have to basically extract all the numbers out of here, all these extra ones and zeros, and then also worry about the matrix that contains 100, 80, and 34. So first, we will have the matrix 1, 1, 1, 1, 1, 0, and finally 1, 0, negative 1. So this is what we're typically calling matrix A. Then we have the little matrix that contains all the variables, x, y, z. We typically call that capital X, and it's all equal to the matrix 100, 80, and 34. And in order to get the variables that I'm searching for, I'll have to multiply the column matrix 180, 34 on the left by the inverse of this guy. So this is the A, this is the X, and this is the B matrix. These are all capital letters. And so I want X, so therefore I got to multiply B on the left by A inverse. So doing that, what do we get for our X? So the X contains the variables X, Y, Z. I'm going to use the calculator to multiply A inverse with the B, and let's see what we get. So first things first, let's check that we have the entries already correct into the calculator. So I'm going to edit matrix A and double check that the numbers are 1, 1, 1, 1, 1, 0, 1, 0, negative 1. So it seems right. Let's check the matrix B. So the matrix B should have 100, 84, and 34, and it looks right. So perfect. We have everything we need. So we're going to go back to the main screen of the calculator, and we will ask for the A inverse matrix multiplied with the matrix B. And in case there's decimals, we don't want any of those. We'll go ahead and use math 1 to turn everything into fractions. And there we have it, 50, 34, and 16. So the answer is 50, 34, and 16. So in other terms, the X, Y, Z triplet that we're looking for consists of the numbers 50, 34, and 16. So what does that mean? What that means is that the fastest machines is making 50 hubcaps per day, right? Remember, X is 50, and X refers to the fastest machine's amount. The medium speed machine, or the just regular fast machine, is making 34 hubcaps per day, and the smallest machine, Z, is making 16. That's the slowest one. Okay, we have example 7. It's a similar kind of situation to one we did previously in the last section. We have a total of 2,500 tickets were sold to a soccer match, and we have children tickets, senior tickets, and general admission tickets. So we'll start by labeling the variables. So we're going to have children tickets, we have some senior tickets, and we have some general admission tickets. So let's see, I'm going to call X the number of tickets that were sold to children, Y the number of tickets that were sold to seniors, and for general admission, we'll use Z. And we know from the very first sentence that a total of 2,500 tickets were sold. So what does that mean? That means that X and Y and Z altogether was 2,500. Now, we know that for the prices, the price of the children tickets were $2. For seniors, they were $3, and for general admissions, they were $5. We're also told that the revenue from the ticket sales was 7,250. So I'm going to take that sentence and the other one all together, even though they're separated, and we're going to put them together. So each child ticket was sold for $2, each senior ticket was sold for $3, and each general admission ticket was sold for $5, and altogether the revenue was $7,250. So that's the end of that part. And finally, we have to translate this middle sentence that we skipped. So we're told that twice as many tickets were sold to seniors as to children. And this means that the number of senior tickets that were sold is twice the number that were sold to children. So again, as a system of linear equations, this looks fine, it's kind of okay, but it does not help me if I'm trying to solve this problem with matrices. So the first thing I'm going to do is rewrite my system with a little bit more organization. So x plus y plus z is 2,500. Then I'll have the 2x plus the 3y plus the 5z equals to 7,250. And finally, for the last equation, I'm going to put the x variable first, so I need to move it across. It's going to be negative 2x. The y is there. There is no z, so that reminds me that I need to have 0z there. And when I move the 2x, there's not going to be anything across, so we'll have a 0 as well. So remember, all the missing numbers are 1s, and this one in particular here is 0 because there is no z in the problem. So as the matrix, we will have 1, 1, 1, then 2, 3, 5, then negative 2, 1, 0. That's the matrix A. And the matrix X will consist of the variables X, Y, and Z. And finally, matrix B consists of the 2,500, 7,250, and finally 0. So if I want to know what X, Y, Z is, I'll have to multiply this column matrix on the left by the inverse of this matrix. So let's do that with our TI calculator. So to get x, y, z, let's record what we're about to do. We need to multiply the matrix A inverse with the matrix B. And keep in mind, this is what we're calling matrix A, and this is what we're calling matrix B. So keep in mind, you're not multiplying the regular A, you're multiplying the A inverse. So let's confirm that we have the numbers correct into our calculator. So if I look at matrix A, the numbers should be 1, 1, 1, 2, 3, 5, negative 2, 1, 0. If I look at matrix B, it should have the numbers 2,500 and 7,250. So it looks okay. Everything is correctly saved into the calculator. I'll go ahead and go to the main screen of my calculator, and I'm going to tell it to multiply the matrix A inverse with the matrix B. And I don't want any decimals, so I'll add the frac command. And there we have it, 750, 1,500, and 250. So in other terms, the solution of this problem is that the ordered triplet x, y, z consists of the numbers 750, 1,500, and 250. So in other terms, we sold 750 children tickets because X refers to children. Y is the number of senior tickets that were sold, so that's 1,500 senior tickets were sold. And finally, Z is the general admission. We only sold 250 general admission tickets to this game.